Yeah. So our next speaker is Rahul Ilango. He's my PhD student. He's awesome. He gives great talks. I can take no credit for any of this. It's all him. Just in case you were wondering. Yeah, go for it, man.
All right. Thanks for the introduction, Ryan. So I'm going to talk today about conditional hardness for MCSP, and the back of I think all of our heads is this question about whether MCSP is NP complete. And my goal in this talk is so that for the people who are maybe not so familiar with the results about MCSP, the hardness results about MCSP, to tell you what the main results we know so far are, kind of what the main techniques are, and what the next steps are. So I think hopefully this will be useful if you want to attack the problem this semester, giving you the background you need for this thing. So I also, because this is a 2-hour talk in the afternoon, I have some trivia, which will be a little fun, but we'll get to that later. So we're on day 2 of Metacomplexity. You guys have seen a lot of Metacomplexity problems. You know, we have the complexity zoo. I think there's also a Metacomplexity zoo, and there are many, many problems here. And I think all of these problems, going back all the way to K complexity, which have a long history, and there are many, many results about them. But today, I mostly want to focus in on this problem, MCSP, your friendly neighborhood Metacomplexity problem. One, because I want to limit the number of definitions that you guys have to keep in mind. So I think by concentrating on MCSP, it will help you guys be able to follow more of the talk and more of the ideas, especially to the people who this is new for. And also because I think all of the major techniques and the main story towards NP-hardness of MCSP can be told via the variance of MCSP and its close brethren. So, you know, there are going to be many results that I won't cover, but hopefully I can get the story across to you using MCSP. Okay, so at this point, you guys have seen this slide or variants of this slide many times, what the minimum circuit size problem is, so I probably won't get into it, but just to do a quick review, you know, you're given this truth table of a Boolean function, you're given a size threshold, and you want to decide, does your truth table have circuits of that size? And something that's going to be important throughout this talk is this question, what notion of circuits are you considering? And we'll see various different types of circuits. For different circuit classes, we have different hardness and different techniques that we're using to prove that the problem is NP-hard. Okay. And as we all know by now, this is a problem in NP that's probably not in P. One thing that hasn't been discussed so far is there are really no non-trivial algorithms for MCSP. In fact, I don't even know if there is an algorithm, as far as I'm aware, that shaves like a constant factor off of the brute force algorithm for MCSP. So it's kind of an interesting problem in that it seems like we can make no progress on algorithmically, and this question of proving it's NP-hard, I think, is especially interesting because like we have like no algorithmic ideas on how to attack this problem. Okay, so this is basically what we know, or the basic complexity of MCSP. Probably, are there any questions about this? Probably this has been covered. All right, so the main open question, as you can probably guess by now, and the topic for this talk is what do we know about is MCSP NP-hard? And I also want to mention there's kind of a bigger question, which is the approximation version of NP-hardness. So is MCSP NP-hard? In this talk, we're going to cover various techniques and partial results that kind of work towards showing is the decision version of MCSP, where you have to exactly calculate the circuit complexity of the problem, is that NP-hard? And I think the techniques we have so far are really building towards showing that's NP-hard. But for some of the applications that we have, like connections to average case complexity and so on, it's somehow more important. I like to call this problem distinguishing order from chaos. We heard it earlier as structure from randomness, to distinguish whether you're given some truth table, which is either really ordered, has circuit complexity n to the epsilon, or it really has very little order, has circuit complexity n to the 1 minus epsilon. And this question is really seems to be more mysterious. We have techniques, and we'll go into later in the talk, Shuichi's result about some partial version of MCSP, which gives hardness of a variant of MCSP with some weak inapproximability. But this bigger question about whether in the large approximation regime, the problem is NP-hard is something we know less about. And so this is kind of the big picture, I think, that we want to be working towards. I think understanding this is what I'm going to tell you about a little bit more about it in this talk. But I think the ultimate goal to really understand MCSP is we want to understand this approximation version. So the roadmap for this talk, I guess my arrow really didn't show up on here, but you can see it over there on the sideboards. So in this talk, I'm going to start by recapping some of the motivation for why we want to understand this problem as NP-hard. And I want to specifically talk about that from the NP-hardness standpoint. And then I want to tell you a little bit about the barriers. And this is probably going to be like the first part of this talk. This first hour of this talk is mostly going to be about motivation barriers and a little bit of the progress we've seen so far. And then the second half of the talk is going to be the results that we have, more about the progress. So why do we care so much about NP-hardness of MCSP? There are several reasons, and we've seen some of them so far. One reason that I want to talk about that we haven't talked about so much, Rahul mentioned it briefly, is it's kind of a very like historically interesting problem. I like to joke that it's a question older than time and space. You'll see why later, time and space complexity classes. And the study of MCSP started in the Soviet Union around the 1950s. So these people were interested in the question of like, which problems require brute force search? What problems can you not solve without just having to go through all the potential possibilities and seeing whether they work? And kind of interestingly, their candidate problem was the minimum circuit size problem, which I think is a really funny because it's like a problem today we still don't know how to beat brute force search even by a constant factor. So this was a really good hypothesis. And this is really before complexity theory was really started. They didn't really have the tools to analyze this question, which makes it really amazing that in 1959, a Soviet scientist named Yablonsky basically claimed he had proved that MCSP is not NP. Of course, there wasn't the language for that yet, but this would be really amazing because if Yablonsky's proof was correct, he would have actually resolved P versus NP before it was even stated. And so at least so far as we can tell, this hasn't resolved the problem. He was really looking at a specific case of algorithms for MCSP.
Wait, why would it resolve? And you said we don't know. Why would it resolve P versus NP?
Because MCSP is an NP, and then if it's not in P, then P must be different than NP.
Oh, that it's not in P. Okay,
yeah.
Okay, good.
Yeah. So he was interested in this question of whether it requires brute force search, and yeah, so he had this. It's probably okay. I won't say much more about that. Although it is kind of funny that in an unfortunate event, Yablonsky actually got into power in the scientific community in Soviet Russia. And so it actually became hard to work on this problem of whether MCSP requires parabolic because it was kind of politically difficult when your boss's boss's boss thinks he's proved that it's intractable and you want to keep working on the problem. So it's something that maybe was not so great for research at the time. And so just to justify my title, a question older than time and space, it took like another 6 years for time hierarchy theorem, Hartmanis and Stearns to define these time classes, these space classes. And then one other, okay, I guess, yeah, you can see my anonymous person on the TVs. One other thing that kind of happened out of this parabol research, which I thought was kind of fun, mention it to you guys, is the scientist XTR, unfortunately, I couldn't find a picture of him, motivated by trying to understand these parabolic conjectures, actually effectively ended up proving that P is not equal to NP relative to Oracle, again, before like NP is really defined, and this is like before Gil-Baker-Solovay. So it was kind of some interesting history.
So the way they refer to it is what? Like the best algorithm is brute force search. That's how they stated it.
Yeah, so there's this survey by Trachtenbrot where he talks about it in more detail, but that's basically how they stated it. Yeah. And okay, in 1973, Levin comes onto the scene with his theory of NP completeness. And as Rahul mentioned earlier, he was really interested in only by extending this theory of NP completeness to graph isomorphism, circuit minimization, or with less hope factoring, that this theory would be interesting. And I think good thing he published it. Apparently he tried for a long time. There's a blog post about this on Levin's blog, which is very interesting. But if you're interested, I can send you a link to it later. And then ... until I want to pull out a quote that Ryan made at the Simon's Lower Bound seminar, probably, I think on this stage 4 years ago, when he was talking about MCSP. And he has this quote: if it's a NP complete, it would have to require techniques that are not like any polynomial time reduction that we have ever seen. I think deterministic polynomial time reduction is what he was referring to in context. But so this is kind of this history. We have this history going back all the way to the 1950s, that this is some problem which doesn't seem like you're able to solve without doing brute force search. And so at least this is a historically interesting question. And, okay, but maybe you don't care about history. Why do I want to show that MCSP is NP hard? What do I care? And this motivation that we've seen earlier is eliminating heuristica. So there's this theorem by Hirahara, a really amazing theorem. I like to call it a Death Star theorem because, NP hardness of MCSP is going to destroy this world of heuristica. We're yet to see whether the Death Star will be operational, but yeah. So heuristica, I guess you were supposed to have seen this talk on average case complexity earlier, but probably you already know what heuristica is. It's this world where SAT is worst case hard, but easy on average. And this is a problem eliminating heuristica, for which there were many barriers, whether they would be like non-black box barriers, relativization barriers, and Hirahara was able to weaponize metacomplexity to get a non-black box reduction. So understanding NP hardness of MCSP, in this case, actually, for this specific result, you need an approximation to MCSP. This was like this order versus chaos problem that I talked about earlier. If you get that, then you can destroy heuristica. So this is one, I think, really good motivation to understanding that MCSP is NP hard, not just intractable, but NP hard. Another motivation that we're going to hear about tomorrow is about basing one-way functions on P versus NP. Here, I think is like, I think this is a metacomplexity dream, but I guess it's also more of a cryptographer's dream. But if you could prove this series of implications, if P is not equal to NP, then MCSP is a hard in worst case. So this is the NP hardness of MCSP. And does that imply MCSP is hard on average? And does that imply one-way functions exist? And this would be really amazing because now you have one-way functions, the foundations of cryptography, based on P not equal to NP. And this has been like a long-standing goal for a while. And you can ask, what progress have we made to this goal? And I think in the past few years, there has just been like an explosion of work on all three of these areas. So I'm mostly going to concentrate on this one area over here. But if you're asking, why should we study the NP hardness of MCSP? Well, maybe it could be important in understanding whether one-way functions, whether we can base one-way functions on P not equal to NP. And as we mentioned earlier, in the earlier talks, there are some theorems that when you state them, they have seemingly nothing to do with metacomplexity, like whether strong lower bounds for UP imply average case lower bounds and stuff like this. And here's another question: P not equal to NP, does that imply one-way functions exist where metacomplexity is popping up as a tool? And so this is another motivation for understanding the NP completeness, not just the intractability. And the last main motivation that I want to talk about is kind of a personal motivation. So I got this. This is the most serious picture of me that I could find to describe my personal information, really conveys. So to me, I think understanding this question, whether MCSP is NP hard, is related to like another long-standing problem, which is proving circuit lower bounds. And to me, I think, okay, let me do this part first. To me, in circuit complexity, when you look at pretty much any open question, either it's been open for 30 years or it's solved. It was solved in the 90s, and so it's really good to have new questions to ask, and in particular, tractable intermediate problems. And so this question of understanding, whether MCSP is NP complete or whether the formula version of MCSP is NP complete, or these various questions about MCSP, they give you tractable intermediate questions, or seemingly tractable intermediate questions that let you study, okay, can I use my formula lower bounds to do this? Can I use my constant depth circuit lower bounds to do this? And by doing this, I think it helps kind of give you these intermediate problems that let you attack this area and hopefully develop new tools. And so to me, that's one of the motivations of studying MCSP, and that's what really drew me to the area. And this is kind of vague, that proving hardness for MCSP can lead to new circuit lower bounds. I'll give you a concrete example of this later, where that kind of happens. But yes, those are pretty much the motivations for why you want to prove hardness of MCSP. So let me just recap them really quickly. So one is eliminate heuristica. Another, base one-way functions on P versus NP. Discover new circuit lower bounds. And the last thing I think is curiosity. I didn't talk about this so much, but I mean, it's a very simple problem. I mean, it's a very basic problem. It's been studied since the 1950s. And unlike thousands of other problems, eluded our ability to prove that it's NP complete or not NP complete. And I think it seems like a basic scientific question we want to know the answer to. And I think I want to know the answer to it. You've all come to this Metacomplexity workshop, so presumably you have some interest in this. I think Levin wants to know the answer to this after all these years. So, all right, so is there any questions about this motivation? This is pretty high level stuff. So, okay, cool. So when I was designing how I wanted to present this talk, I was thinking about whether I want to tell you about results first, the progress we've made, whether I want to tell you about barriers first. And it was a tough thing to resolve, but I ended up going with barriers first, because what I want to do is I want to tell you about the barriers, and I want to tell you about what techniques that might inspire. And then when we talk about results, I can show you, okay, here's where we use this technique, here's where we use this technique inspired by the barriers. So that's my goal here. I want to tell you a little bit about the barriers, why this problem is hard to resolve, and that's going to kind of suggest some techniques that we're going to see in the results section. So this is why has it been so difficult? Okay, so one of the primary conclusions, I think, of MCSP research over the past many years has been the limits of deterministic reductions. And this has a pretty natural intuition. So unfortunately, the sad state of circuit complexity is that we don't know explicit hard functions. I've tried, which isn't saying much, but many people have tried, and unfortunately, we don't know whether explicit functions require large circuits. And for the purpose of proving that MCSP is NP-hard, this is particularly annoying because it means we don't really have non-trivial no instances of MCSP. Like we don't know how to produce like a single no instance of MCSP, at least in a uniform way, such that it can't be solved like kind of really quickly by a brute force algorithm. And there are various ways you can formalize it, but the conclusion of this is it's going to be really hard to design a reduction with this constraint. If you don't know what a single hard instance of the problem, like how are you going to get a reduction from SAT to this problem? It seems really difficult. And there are many works, I think these works give particularly good consequences that basically show that if you had a deterministic polynomial time reduction, under various guises, many one, Turing, and so on, that's going to require some sort of breakthrough, something that maybe be it circuit lower bounds or x not equal to ZPP. And in fact, I'll give you two examples of these theorems. So this is by Murray and Williams. Any many one deterministic reduction from SAT to MCSP, that's going to imply x not equal to ZPP. But for the purposes of this talk, it doesn't really matter what that problem is. It's just some long-standing open question. We believe the answer to that question is true, but we don't know how to show it. So this is an example of how getting a deterministic reduction, that's something that we think is beyond us right now. And there are some extensions to Turing reductions, work done by Sachs and Santhanam, which also show that implies circuit lower bounds. And there are various other results here. I don't want to list all of them, but I think the takeaway for this workshop, and when you guys are working on this, is that, okay, deterministic reductions, that seems like something that's difficult to get away with. And this naturally points to a technique of randomized reduction. So we don't know how to deterministically come up with a circuit that with a function that requires large circuits, but if you're allowed to use randomness, well, I can randomly pick a function and then it's going to require large circuits by a counting argument, basically. So what if we are allowed to use randomized reductions? What can that can that help us in proving NP-hardness of MCSP? And the second technique I want to talk about here is sub-exponential reductions. It turns out that this logic here, that if you had a reduction from SAT to MCSP, it like forces you to kind of have circuit lower bounds or some new complexity breakthrough, kind of breaks down in the sub-exponential regime. And I'm going to give you some intuition for why this is true later. So if it doesn't make perfect sense right now, don't worry about it. Ask me about it when I come back to it. I think that'll actually probably be in the next section, next hour of the talk. But it turns out that this kind of logic points to these two techniques. So it suggests, and we'll see this later, randomized reductions coming up and sub-exponential time reductions coming up. Any questions about this or stuff I've said so far? And the second barrier I want to talk about is oracle independent reductions. I think this is something that hasn't played as much of a role in the literature as maybe the work on deterministic reductions, but I wanted to bring this up because there's this result that is like the best, this result by Hirahara, which is like the closest that we can get to MCSP being NP hard. I'm going to tell you about it later. It turns out that this ends up being a barrier for that result. So I want to tell you a little bit about that. You seem skeptical, no? Or no? Okay, okay. Oh, okay. Okay, so let me tell you what an oracle independent reduction is. And so this is something introduced by Hirahara and Watanabe in 2016. And basically the definition of an oracle independent Turing polynomial time Turing reduction from NP to MCSP is that this problem MCSP to the A, I'll tell you what it is later, but for now it's just some problem related to MCSP, that no matter what oracle A you put here, that SAT is NP to the MCSP to the A. So again, I haven't told you what this thing is, but I'll tell you about that next. But it's saying that your reduction, it's not just proving that SAT is NP to the MCSP, but it's also actually proving that SAT is NP to the MCSP to the A. And so one thing about this definition that's a little weird is that like this, we're saying this is a reduction, but here this is just about membership in sets. Don't worry about that distinction for now. It's just and so what is this problem MCSP to the A? You might be able to guess what it is. It says that if you fix some A oracle, you'll now add A oracle gates into your circuit basis. So for example, it could be allowed AND gates, OR gates, NOT gates, and A oracle gates. So these oracle gates could be like SAT gates, they could be QBF gates. And this model was studied in prior papers, for example, by Allender, Holton, Cabinets, and Allender, Berman, Kuski, and Melkebeck, and Ronberger to show hardness. But in this oracle independent reduction section, it was introduced by hard. And this is different from relativization, but let me come back to that later. What I kind of want to say is that what does it mean for something to be an oracle independent reduction from NP to MCSP? It kind of means it's some reduction that doesn't care about what gates you have. You know, as long as they're like a finite number of gates, you can have AND gates, OR gates, NOT gates, and then, you know, whatever function you want, you can add that into your basis, and my reduction doesn't care. And so we say a reduction is oracle independent if this is true. And so you can ask this for any language L, but I just plugged in SAT and NP. Are there any questions about this?
So wait, this is the same reduction. It doesn't depend.
Yeah, okay. So the way that I've defined it, actually the reduction isn't playing a role. It's just a question about set membership, right? But you could imagine a reduction. Yeah, does the same reduction show that? And in fact, this is what's kind of happening with Shuichi's result that we'll talk about later. Not for MCSP star, but KTP star.
I think Hirahara and Watanabe showed if the total is the same, if you consider the same reduction or the different reduction.
Oh, I see.
So they're equivalent.
To the quantifiers, it doesn't matter what order the quantifiers are.
Somehow intuitively think that you could just, you know, for all oracles, that means you could have an A that like targets this reduction.
Yeah, exactly. And
So
in fact,
how does this-
that's what they'll use this. Like,
Oh, okay.
Right, and so the barriers that they showed is that, in fact, there is no deterministic oracle independent reduction from SAT to MCSP. And this is kind of using the thing that Ian was talking about. Specifically, you could imagine choosing some oracle A that kind of targets your reduction, says it's not going to work. And
What limitations are on the Oracle A?
no limitations. It's any. I mean, it has to be like a legitimate function, but
It's a circuit or like,
it could be like stat. It could be QBF. It could be p-space. Or sorry,
It's a language.
it's a language. Yeah. But there
it has to be a decidable language?
I guess no, it doesn't have to be decided.
No limitations.
No limitations. Yeah. So yeah, this is really, it's like and that's why this kind of having an Oracle independent reduction is something that's kind of strong. It's saying that like I really don't care about the circuit model in the sense that like you can add any, maybe even an undecidable gate into your circuit model, and that still will get this hardness reduction. And so here Hara and Watanabe, they showed that there can be no deterministic Oracle reduction from SAT to MCSP. And they even show a barrier that is maybe more interesting for us, is that there's no randomized one query Oracle independent reduction. So it says like there's no, even a randomized many one reduction you can't get. And so, okay, this slide is a bit technical, but the takeaway that I want you guys to have, if you guys try and prove hardness for MCSP, is that you're going to have to keep this in mind. You're going to need to use circuit lower bounds techniques that somehow depend on the gate set in some way, but it just needs to be, you know, that doesn't work for all oracles A, or maybe you can use multiple queries there. So
A needs to take a lot of inputs, right? It takes n bits.
yeah. So
Like a binary gate.
yeah. So what you do, you get, I guess, is you get like an infinite number of gates for each input. For each input length, you get one gate that solves that problem on that input length. Did that make sense? Like, so what's going to happen is you're going to get your gates that you're going to allow to use is, let's say you get OR on 2 inputs, you get NOT on 1 input, you get AND on 2 inputs, and you also might get SAT on 1 input, and then SAT on 2 inputs that you can all use in the circuit. Did that answer your question, or? Yeah. Okay. All right. Great. Yeah. Any other questions? Yes.
For the exact MCSP or some approximate?
That's a good question. Actually, the deterministic thing probably should work for the approximation version. I'd have to think about the randomized one. Right. I mean, if you prove it for an approximation hardness for approximation version, it's going to prove it for the non-approximation version. Oh, you're saying could you get stronger hardness for the approximation version?
Saying if the barrier only holds for proving that the approximation version.
Oh, I see. No, but this definitely holds for the
This holds for
non-approximation version. I see. I understand. Yeah.
Is there some reason to believe that randomized, say, constant query Oracle independent reductions have significantly more power?
Yes, I think this is a good question. So one thing I should mention that I was going to mention next is we actually do have Oracle reductions that are not Oracle independent. So for example, Allender and Hirahara, I think the MKTP, the debt to a MKTP reduction, that's not Oracle independent. Right, but this question of multiple queries, I think that's something that would be important to understand with respect to Hirahara's new result on partial MCSP. Like, how can we make this reduction not Oracle independent? And, yeah. Okay, great. Any more questions?
Is that reduction for partial MCSP Oracle?
Yeah. Okay. So I'll mention. Actually, let me. Let me talk about that in the next part when I talk about that. Actually, talk about that reduction. Yeah. Is this true for the hardness of K-poly? I think so. The deterministic part, that's definitely going to be true. The randomized part, I have to think about it. Yeah, sure.
Last question, but this is true for MCSP star too, or?
Yeah. Okay. So the answer to Ryan's question was, there's this problem that I keep referring to is a partial MCSP that Hirahara has made progress on. The techniques there for partial MCSP, it's actually somewhat unclear if it's Oracle independent, but for like, he shows that a lot of problems are NP complete.
I'm asking, like, this is barrier hold for MCSP star too, like the Oracle independent.
Oh, I see. Yeah, it doesn't. In fact, it doesn't. Yeah.
So we can't have like NP-hardness. I mean, or via like deterministic adoption or something. for MCSP star.
Apply deterministic reductions. Now, the previous barriers on the previous slide will apply to MCSP star. Maybe I'll move on. I think this is not such a crucial thing to understand, but right now. But if you do end up trying to attack Hirahara's question, I think it's something to keep in mind. Okay. Another barrier you could imagine is proving hardness for MCSP. You know, it can help you eliminate heuristica, and there are some barriers related to that. There are some black box barriers, and there's some relativization barriers. But actually, so we have results that do get past both of these things. So as I mentioned earlier, the worst case to average case reduction for NP that Hirahara shows is non-black box. And this MCSP star result that Hirahara has just shown is non-relativizing. So even though that these are barriers to eliminating heuristica, I don't think it's out of the question that we were actually able to prove the NP hardness needed to do it. So I wouldn't, my personal take is I don't view these as much of a barriers as maybe the previous students. Okay. And then the last kind of barrier that I want to keep in mind is, well, maybe the statement's just false. That would be a big barrier. Is it possible that MCSP is just not NP hard? And so I think the general consensus at this point is that probably the problem is NP hard. At least I'd venture to say that. I don't know what other people would say. But I do want to say that there is some evidence, maybe not strong evidence, but there is some evidence that maybe the problem could be NP intermediate. And so what does NP intermediate mean? NP intermediate is some problem that's in NP, but not in P and not NP complete. So it's some problem that's difficult and it's in NP, but it just doesn't happen to be NP complete. And there's this theorem by Ladner which says that if P is actually not equal to NP, then infinitely many NP intermediate problems exist. And MCSP, I think, was a potential candidate NP intermediate problem for a while, and there's some reasons for that. So one result that shows MCSP kind of works towards MCSP being NP intermediate, depending on how you define it, is this result by Murray and Williams, which shows that under certain types of reductions called projections, which we actually saw earlier today, MCSP is just unconditionally not NP hard. And so if you defined your NP hardness with respect to these relatively weak reductions, which I should say, like almost any NP complete problem that you name is going to be NP complete under these n to the 0.49 time projections. I think like in that paper, the only counter example you guys couldn't, or problem you couldn't do was like subset sum or something like that. But almost every other NP complete problem that we know is going to be NP complete, not just under n to the 0.49 time projections, but like polylog time projections. So, but to me, I mean, my opinion on this is this is really about the weakness of these reductions more than the NP intermediate problem, NP intermediateness of MCSP. But you know, that's my take. I mean, obviously you could think the other way about. And another result that I want to mention is by Allender and Hirahara, who showed that if you take a really, really large approximation to MCSP and one-way functions exist, then this problem is going to be NP intermediate. And this is cool because they just on this like one-way function assumption, you can show that this problem is not NP intermediate or is NP intermediate. But I want to stress that this is maybe not so surprising, because like under ETH, this is such a large approximation that even like brute forcing the answer is going to break ETH. So this is a problem that maybe you'd expect to be NP intermediate. Okay.
So what's the definition of NP intermediate? Like what type of reductions do you consider?
Oh,
Black box or non-black box also?
I see. You're saying, yeah, I guess to really define NP intermediate, usually it's defined with respect to
Like
black box reductions. I guess Ladner's
like a Turing
theorem,
reduction or? I don't know.
he said many one reductions.
Okay.
I understand this was Turing reducibility.
Wouldn't you have also
Like if you play with parameters, wouldn't you have also that some variant of sat is NP intermediate? Like if I would say sat on n to the little o1 variables, it's probably n.
NP intermediate, yeah, based on a similar ETH thing at least.
Because I cannot reduce sat on n variables to sat with n to the little.
Yeah, exactly. I think that's right. And you actually can prove similar results. I think in this paper you mentioned you can prove similar results for clique as well, right?
I'm having trouble hearing.
Oh, sorry. Okay, it's not so important, but yeah. So just as a recap for barriers, for deterministic reductions, we know it's going to require a breakthrough, so you're probably going to need to use randomness. Oracle independent reductions, you're probably going to need some fact about the gate set in some way, but this is not going to be such an exotic thing. We have reductions which are not Oracle independent, and there is some limited evidence that the problem is NP intermediate. So now I'm going to talk about progress we have towards showing that the MCSP is NP hard and for various problems. Is there any questions about the stuff I've talked about so far? Yeah, Alex.
Yeah, is there a universe in which you get NP hardness with respect to randomized reductions, but the problem is not NP hard with respect to deterministic reductions, or is it more of a question of what we're capable of proving? Does the question make sense?
Yeah, well, okay. Let me give you an answer and let me see if it answers your question. So if you believe in strong enough circuit lower bounds, like a randomized reduction is going to imply deterministic reduction.
Good, okay.
So
it's just a question of what we can prove. Yeah.
Yeah, it's just a question about what we can prove. Or I mean, assuming it is NP hard. Yeah.
Do we have like a candidates construction? Like if we knew how to prove lower bounds and we had an explicit hard function.
Yeah. I think this is a great question. I think so. As far as I know, there is no candidate construction. In fact, for some time, I spent some time trying to answer the question, like, can I come up with any conjecture? You know, let it be ridiculous. You know, like the optimal circuit for doing something looks exactly like this, and then based on that, can I prove MCSP is NP hard? And I wasn't able to do it. I think it's an interesting question. Can you come up with even a contrived hypothesis that isn't like obviously like MCSP is NP hard, which would imply that MCSP is NP hard? Is there any, like, even if I let you make a reasonable conjecture, can you show it? So as far as I know, there's no candidate example, and I think that's an interesting question. Any other questions? Okay, and I think that brings us to our first trivia segment. And so as you can see over here, we have a list of wonderful prizes that you are not allowed to eat in this room, I've been told. So, but you can take them home with you. So if you're interested in any of these prizes, you're going to have to answer my questions. So this is trivia about Euros Hartmanis, who sadly passed away in the past year, I think. And so Hartmanis, as I mentioned earlier, was one of the co-authors on this paper that introduced time classes and space classes and the time hierarchy theorem. And so my question is, when Hartmanis and Stearns proved the time hierarchy theorem, what was Hartmanis's affiliation? No, don't shout out the answer yet. There's going to be a multiple choice. We're gonna have yeah. All right. So A, Cornell, B, IBM, C, General Electric, D, Rutgers. So who thinks the answer is A? Raise your hand. Remember, there's cash on the line. I mean, non-cash prizes on the line. All right, Greg's thinking A. Who thinks B, IBM? All right, we got some. Okay, I guess what I'm gonna do is I need to. So Greg, what's your opinion for Cornell? You have any logic behind that?
I mean, I know he was at Cornell for a while. It seems like with high probability he was there back then, just because I haven't heard of him being at the other places, but I'm not 100% sure.
Okay. Who thinks B? Who are the people who thought B? Oh, they're all gone. Okay. Do you have any reason for choosing? Okay, but you think B. Okay, you are the people who are going to get the prizes, by the way. So if you guys are right, who thinks C, General Electric? Oh, okay. All right. Who wants to be the representative? Okay, Oliver. Do you have any logic?
Like it wouldn't be there if that wasn't the answer.
Oh, it's like me. Don't play the game, play the player. Okay.
My logic is golden.
Oh yeah. All right. Who thinks it's Rutgers? All right. So the answer was General Electric. This was kind of surprising to me. I just found this out recently. I was reading. There's an excellent obituary on Cornell's page, and it talks about how he was at General Electric, and I think this is something that's kind of funny, that the birth of computational complexity occurred at a General Electric's lab. I've never heard of it. I didn't even know that they did research like that. I think that's very cool. So Oliver, I think you were the person. What prize would you like from the list?
I'll take the almond joy.
Almond Joy. Okay. All right. This. Oh, I think that was on you. All right, we got one more trivia question before we resume the talk. This one's about Albert Meyer. So Albert Meyer introduced the polynomial hierarchy along with Larry Stockmeyer. He graduated from his PhD in Harvard in 1972. What year did he become faculty at MIT? Is it A, 1969? Raise your hand. No one thinks A. All right. Is it B, 1971? All right, we got a couple. Okay, Chanchi, you have a reason for this? Oh, strangest answer. Okay. It's 1972. Well, okay, Greg, you have any reason?
Because I didn't see anyone else raising their hands for this. 100% chance of getting the candy.
All right, and D, 1973. Amlin, any? Yeah. All right, answer A, 1969. So I have sources for this. The source is the MIT website, as well as the math genealogy page and Wikipedia. I have no idea how this happened. Maybe somebody here knows the story. I guess not, because nobody chose A. Well, he graduated from his PhD in 1972, and as far as I can tell, he became faculty at MIT in 1969. So that's an inspiring story to us all, I think. And so one more question. When did Albert Meyer's first PhD student graduate? Who thinks A, 1969? All right, do you have a logic?
No, I just see the 196.
Oh. Ah, I see. All right. B, 1971. Do you have logic?
It'll be fun if his student graduate first.
1972. Ian, you have some.
His first student was Albert Meyer himself.
1973. All right. I guess. Greg, you have any?
Yeah, I mean, I also raised my hand for 1972, but you didn't call on me.
Okay, so the answer is 1972. I'm curious to know how far from his own graduation his student graduated. Again, this is based on the Math Genealogy Project, so those are my sources. If somebody can figure out the story behind this, I think it'd be very fascinating. Ian, can you see over there? Yes. Which I should cross off some stuff. What did you get, Oliver? You got the Almond Joy?
Yeah.
All right, that's gone.
What's in the back of the room, actually?
That's gone. And Ian, what would you like?
I will take, I think that says 2 pints of Reese's Pieces.
Okay, Reese's Pieces. All right, I don't know. Okay. You might lose out on your prize for that. Right, okay, here you go. These are 2 pieces, not 2 pints. That's my roommate over there, Fran, so might hear about that later. Okay, so I'm gonna talk for another 5 minutes and then we can disperse. So I'm gonna tell you a little bit about the progress to hardness and the things that I want to convey to you about the progress we've made on proving the NP hardness of MCSP is that there's kind of 3 prongs of attack. In fact, really there's 2 prongs of attack, and this thing is something I want to mention because that's where the field has kind of gone. I'm going to give you an opinion on this, and what I'm going to talk about right now is kind of cryptographic hardness results. And these cryptographic hardness results, they're kind of older results, and seemingly they're not so related to the NP hardness of MCSP. But as we'll see later, it seems it's the way that the field and techniques are moving. It seems like cryptography is becoming more and more important to proving NP hardness of MCSP. So that's why I want to tell you a little bit about this cryptographic approach to proving hardness for MCSP. So it's with the motivation of understanding NP hardness in the back of our mind. Okay. So this is something that we've actually seen a couple times now, that one-way functions imply that MCSP is intractable, but let me just walk you through it again, because we're going to use it in the next slide as well. So there's this theorem, I guess, so who you credit to, it's Cabinets and Tsai, who redefined the MCSP problem after many years, observed it, and I guess they credit Razborov and Rudich, and some people credit HILL as well. Anyway, there's this theorem that if one-way functions exist, then MCSP is not NP. And let me just mention, I don't think this has been mentioned previously, but this actually shows like really strong inapproximability of MCSP, at least under cryptographic assumption. Basically, if you, depending on how strong of cryptography you believe in, do you believe in like sub-exponentially secure one-way functions, maybe even exponentially secure one-way functions? If you believe that like the best possible one-way functions exist, you're essentially gonna, this theorem is gonna show that MCSP is basically completely inapproximable if the brute force algorithm is pretty much optimal. So we'll see that now. I'm gonna recap some of the proof. So the proof idea is as follows. If one-way functions exist, then they're gonna imply some pseudo-random set. This is gonna be based on like, if you're familiar with cryptography, it's gonna take your one-way function, turn it into a PRG, take your PRG, turn it into a PRF. And then after that, you can take like an initial segment of the PRF, but if you're not familiar with that, don't worry about it. You basically get a pseudo-random set of truth tables with the following properties.
What is a pseudo-random set?
Sorry, what was the question?
What is a pseudo-random set?
What?
He's about to say.
I'm about to define it. One-way functions imply the existence of a pseudo-random set of n-bit truth tables. So this is just some set of truth tables with the following two properties. These are going to be n-bit truth tables. Every truth table in this set has low circuit complexity. So let's say complexity n to the 0.01. You can make that constant as small as you want. And the second property is that they're going to be pseudo-random, that no poly n time algorithm can distinguish when you take a uniform element of S from a uniformly random n-bit string. So cryptography just guarantees this. If you're not familiar with cryptography, then you can take it on faith. Otherwise, you can do the construction via GGM and Hill. And now, okay, we're pretty much set up to attack this. As Valentin said earlier, we can kill the PRG with MCSP. A random string has complexity n to the 1 minus little o of 1. So now, since every string in this set has low complexity, and a random string has high complexity, MCSP can distinguish this set from random. And so by the pseudo-randomness of this set, MCSP cannot have a poly n time algorithm. And if you assume you have sub-exponential one-way functions, now you'll get that instead of there's no polynomial time algorithm, there's no sub-exponential time algorithm. And you'll get that there's no sub-exponential time algorithm for MCSP. And notably in this proof, I just want to emphasize that even this question that I mentioned earlier about like order versus chaos, it shows that this is intractable.
So is this like the main source of that? This easier problem is still NP hard? Are there other things?
Yeah, I think this is the main source of. In fact, yeah, I think we're on the NP hardness standpoint. We haven't really gotten to the point where we can talk about this. We're getting closer. I think in the past few years, like yeah, okay, I'll talk about it later. But this is the main source of hardness. And so there's this, as I mentioned earlier, there's this technique that's being used more and more in these NP hardness reductions, which is using cryptographic ideas. I think this is the first place where cryptographic ideas prove the intractability of MCSP. Okay, and then I also want to mention this hardness for statistical zero knowledge. So if you're not familiar with statistical zero knowledge, maybe you're familiar with zero knowledge. Statistical zero knowledge just talks about some version of zero knowledge where you care about information theoretic security. If you don't know what zero knowledge is, or you don't know what information theoretic zero knowledge would mean, don't worry about it. I'll just give you some example of some problems in them. So graph isomorphism is probably the most famous problem, but there's also a bunch of cryptographic problems like quadratic residuosity, approximate choice vector problem, some version of discrete log. And so all these problems that we think are cryptographically hard are in SCK. And SCK is some class that under widely believed de-randomization assumptions is in NP intersect. And Allender and Das showed that every problem in SEK reduces to MCSP, and we heard a little bit about this morning, not quite this theorem statement, but a version of it. And this right now for MCSP proper, the original version of MCSP, this is basically the best hardness we know under the usual types of black box reductions. Use this class SEK, which is probably not, probably outside of P if you believe in this various types of cryptography, that everything in SEK reduces to MCSP. And so, you know, I'll tell you like briefly, like one of the ideas behind this reduction, and this is going to be like very brief. There's this complete problem for SEK. There are many complete problems, but one complete problem basically says, you hand me two circuits, and either those two circuits, the distribution induced by them is basically the same. Their statistical distance is small, or their ranges rarely intersect on average, whatever that means. So you either get two circuits whose ranges intersect a lot of the time, or they don't intersect a lot of the time. And all the intuition I'm going to give you is to solve this complete problem, you can use MCSP's ability to invert one-way functions to test whether circuits have similar ranges or not. So the idea is, you know, you run the circuit on one input, you get some element that's in the range of the first circuit. Then you use MCSP's ability to invert functions to test whether that's in the range of the second circuit. And things are kind of set up nicely so that you can carry this out. There are some more details about this, but this is like an example of how you use MCSP's ability to invert one-way functions in order to get hardness. Yes.
Can we just strictly use results that is hardness of SEK implies one-way functions?
Yeah.
And then the previous result? Or?
And then you, yeah. So another way to do this, I guess there's this result by Ostrovsky, which says that if, okay, let me get the direction. What's the direction?
SEK is hard. Then you have auxiliary input one-way functions.
Yeah, exactly.
You need average case hardness for that, I think.
No, auxiliary input one-way functions.
Oh, okay.
But auxiliary input one-way functions are good enough for
breaking it with MCSP. Yeah, that's another way to do it. Yeah, exactly. And this is another, or this is an example again of using randomized reductions. The randomness here is used to like sample from the distributions and invert. This ability to invert one-way functions is some sort of average case notion. So you're going to need to use randomness. And this is another example where we're using cryptographic tools to understand the complexity of MCSP. So these are two techniques that I want to emphasize. And I think that will be the stopping point for this talk. Okay, let me think, is there anything else that I want to mention about SEK? Yeah, okay, I think that's it. And are there any questions?
Excellent. Questions, Rahul? I have a question for you. What is what after? Questions for Rahul.
For you. You want to ask Ryan?
Any questions for this guy?
All right.
Any more candy?
There'll be another trivia segment, by the way, so you should come
That
to
was
the
my
next
question.
one. Oh.
How much? Okay, more trivia. Okay, good.
There'll be more trivia midway through the next one.
All right. Well, see you again.